Just a quick recap. I know it's not the maximum screen yet, but a quick recap of what the stuff we've talked about. And of course, we've been talking about machine learning, and we started off by talking about the popular learning algorithms. We did say we may or may not touch on SVM. I don't think we'll touch on SVM, but at least we will touch on K-means algorithm. We intended to talk about K-nearest neighbor. I don't think we talked about it in this class. So we will start off by talking about K-nearest neighbor, and we'll talk about the Bayesian algorithm as well. And we will touch on K-means, but then we'll have catch-up materials if they need. But let's try to see how things go with the session today. Yes, we started off with hot dogs, not hot dog, and other things, but we were particularly interested in our beautiful graph. Where is it? Let's go back to the map. We were interested in this map where we actually modified it slightly by saying that yes, we had our supervised learning algorithms that we've been looking at, and there is regression and there is classification. So let me do this on this slide. I will try to, let me try to do this so it doesn't record over it. Just bear with me. Slideshow, record. Good. So one thing I would want to clarify though, yes, there were some confusions around the use of the word regression here, and of course regression there as well. Sorry, I keep getting some glitches. I don't think it's from my side. If you can't hear any glitch at your end, I'm completely happy to continue. So with under supervised learning, we said there is regression and there is classification. And within the classification, we've got binary classification and we've got, what was the other one? So we have binary, what was the other one?
Multi-classification.
Yes, multi-class classification, wonderful. People are awake. So let's put that MC and then BC, right? And what we were saying was that under binary classification, we have decision trees and we've got logistic regression. Just don't let the word regression after the logistic confuse you. It's basically still binary in nature. So we have a graph that looks like that or distribution that looks like that. And we said we use a sigmoid function to find it. And there was question around threshold and other things, but it still fall within binary classification, right? Then linear regression will fall under regression because it's got like that continuous data distribution on there. Are we okay up to this point? Yeah, I think it's important we understand this because we spent quite some time on trying to decipher whether why logistic actually fall under binary. And I think it's the confusion was just coming from the name regression on there. But for now, we are okay and happy with that. So again, we step back out from the slides and go through where the things we talked about. We talked about the binary tree, so we've touched on the trees, and also, well, logistic and linear, we've touched on them in previous weeks as well. And that will take us to the K-nearest neighbor. So I will start off the recording from this side. I believe we covered all these up to this point for some example. So that'll take us to K-nearest neighbor. I'll just do some slight tweaks to the slide as we go on, meaning we might not use every single slide, but we'll still do some jumping in between because I plan to cover K-means after K-nearest neighbor simply because they're mostly confused with each other. But then we will jump to cover the Bayesians before we come back to K-means. So still here, still under supervised learning, we want to go into classifications, not regression, classification, and we want to look at KNN, right? So I'll be back here. And we'll start our recording from this point. Are we okay up to this point? You can hear me loud and clear.
Yes, please.
Okay. So we're saying that one of recording starting in 3, 2, 1. Yes, okay. So we're saying that one of the best ways in machine learning to actually learn. Sorry, let me get a pen up. Yeah, there we are. So one of the best way to learn more about your data is by classification, right? Which is so fall under supervised learning that we already know. So, but we want to make use of known information because it's supervised, so we understand the data to a certain level and we have labeled it to a certain level. And we want to try that to use it to group a bunch of data together. So we can say that's one grouping, or basically identify the odd one out or the elephant in the room. And then we have another type of data, yellow not very clear because it's still on the yellow background. I don't know why I chose that. Then we have another sort of group, but this is based on information that we know. So there are certain characteristics or certain features that we can easily identify, and we are using it to sort of classify. We're using our model to sort of classify whether, yes, it is a red, whether it's a yellow, or whether it's a white in this particular case, for example. But this is based on information that we already know, so it is supervised. And one of the common multi-class classifications, so we had our binary under classification, we had our binary, we've looked at our regression, and we have looked under, so let me put the binary there, sorry, this is classification, CL, and then this is binary classification. We've had our logistic regression, and also we have our binary trees, right? We just want to look at the multi-class where you have several features or can be countless number of classification. In this particular case, several colors, not necessarily yes or no. And we want to say where we have our multi, one of the algorithms that we want to look at, or one of the most popular of them, is the KNN, where NN is the nearest neighbor. We okay up to this point, yes?
Yes.
Good. So basically similar to what example we just talked about, things like color. We already know the color, so we can label them and feed it into our model. And the model will try to look at unknown data to try to also classify them based on the classifier that we create out of it.
Please, I can't hear you. Please, can you,
Please ask.
please, could you repeat what you just said?
Oh,
I
okay.
think your voice was. Yeah.
My voice is alternating going up and down again, right? So look, just bear with me 1 second. How about now? That's tweeting. How about now? Is it better?
Yeah, after that.
Okay. So pretty much the point that we made here, we have already explained with this at this particular point in time. We are talking about supervised learning, right? Yes?
Yes, yeah.
Yeah, which means that we know we have our training set, which we can easily say that from the training set, if you see this, that is pink. If you see that, that is blue. If you see that, that's green. If you see that, that's white. And we'll try to come up with a model that if we feed a new test data into it, which is the data the model has not seen before, it will be able to say, okay, that is, you belong to pink, you belong to maybe blue, you belong to green, you belong to white. Does that make sense up to this point?
Yes, up to this point, it makes sense.
Good. Good. So that's sort of the main thing we have said. And we have, of course, said K-nearest neighbor is a type of multi-class classification that we are actually doing. Right. So we say that I'm just starting the recording again, and we have our pen back up. So actually, KNN is an instance-based machine learning algorithm, or it's actually what we call lazy learning. Can you see? Ish?
Yes, please.
Okay. It's just basically lazy learning, L-A-Z-Y learning. And with lazy learning, basically it's called lazy learning because we're doing the bulk of the computation It's all happening in an instance, all happening at the same time, right before we want to do our classification of the mode. So we just basically do all the computation, try to do all the computation at the same time. So we try to find all the classes at the same time. We don't do it sequentially, right? It's not like the tree where we start with the roots, then we branch, then go to the next step. This one, we're trying to do everything at the same time, right? So the downfall of this is that if you have a huge chunk of data, right, you are trading off computational power because you demand a lot of computational power. So you need a really powerful computer to do that. You need a powerful machine to do that. So it actually has a high demand of computational power. Okay, so supervised learning, comparing it information with what we already know, with what we don't know. But at the same time, it's lazy because you're trying to do everything in one go just before your classification. But because you're doing that, when dealing with large chunks of data, you really there's a high demand of computational power. Are we okay up to this point?
Yes.
Yep. So
Yeah.
if so, pretty much that's the whole thing that these sort of points we're going to make with emphasis on the computational power on this slide. So we can start off by looking at an example. Hopefully you can see the screen. Can I just do a simple eye test or a small eye test to see what's inside the screen? Do we know what kind of thing it is? Can we tell? So I don't have to draw the outline. So we have a dog. It's just a dog, right? So it's just we're taking a scenario of maybe you are in an animal shelter or pet shop. You have different breeds of dogs together in one room. So we take the example of an animal shelter. I'll just use that from now onwards. And what we want to do is to try to classify the breeds of dogs. But this is based on the information that we know or some of the features we know for dogs. Sorry, was that a glitch or someone was trying to ask me a question? Can I?
I don't, you can go on, you can go on.
Okay, thank you. Right, so there are hundreds of different breeds of dogs that we can classify into. So we have the hundreds that we know of or several that we know of. So not only are these the possible outcome with the different breeds, also we have to bear in mind that we have mixed breeds of dogs as well. So basically, we take the unknown dog and we compare it to the known dogs or the known breeds that we have. Pretty much think of it as carrying the dog around the shelter and comparing it with each one that you know of. So just compare it with a different breeds of dog, and eventually we find out that this incoming one actually has some similar features, right, as the unknown one. So we've got some similar features as the unknown one. At this particular point in time, whilst walking down, sorry, it's present, so it's back up. Whilst walking down, we've reached the point where we are actually closest to this particular breed. And also we are closest to it, not just more or less in distance, but in terms of some of the features. You can say hair length almost the same or the shape almost the same. And hence we say we have confidence that this particular dog or the unknown dog breed more or less belong to this particular group. That's just an example. All we're trying to think about is that, okay, which of the neighboring dogs or the dogs that we've seen so far have similar features as the dog that we want? And you can think of it in terms of distance. So let's say we take our data points. These are our ground truth data points, right? And we distribute them in the Cartesian plane, for example, in this particular case, where we have several data points with ground truth that we're looking at. And we say, for this particular data point, we really want to find out where it belongs, right? The same thing as we look at dog features to see which one is likely or which group we should put, or which kind of breed is likely to be. We can look at maybe its neighbors. and then we try to find out which of these neighbors it belongs to, or which of these particular neighbors in terms of distance is closest to. That's why we say nearest neighbor, where K is the number that we are looking at. So KNN, the K in this particular case is how many neighbors are we looking at, right? So if we say K of 2, then we are looking at 2 of closest neighbors to group them with. So again, walk through them, quite similar, just same explanation as we've had, and then we can eventually more or less settle on one that we say it belongs to. So if we come back to the dog breed example, for example, we can actually say we take in 2 predictors. The predictors are the features that we are looking at, right? We say we take in 2 predictors to try to identify what kind of dog breed it is. So can be many, but let's take 2 for simplicity. So we say the 2 predictors we are looking at are the hair length of the dog, and then also the weight of the dog as well. So we're just looking at 2 things, the hair length and the weight. So if we take the ground truth data from our data set and we distribute them evenly, so we distribute them based on the hair length and the weight. So if we say this dog, the weight is maybe, I don't know, 30K, some random one, 30 kg. And that maps to a hair length of maybe 5 inches. Not sure whether it's realistic, but let's go with that. That will give us this data point, and we have several distribution based on the nature of our data into the XY plane. Then we bring in the unknown dog or unknown data point that we really want to find. And if we say K equals 5, that means we are putting a circle among the 5 of its closest neighbors. So in this particular case, for that unknown data point, sorry, it's frozen. Just give it a second for it to come back. So for this unknown data point that we have, again, it keeps freezing. So it was doing well earlier. Can I double check to see whether you can all hear me?
We can.
Good. So we have the 5 circled around this particular unknown data point, and then we try to find out, okay, what kind of dog breeds are closest to it, right? So we have the neighbors now, and all we want to say is that among its closest neighbors, in terms of distance, using the Euclidean distance, what kind of dog breeds are closest to it? Hence the idea of the neighbor is more or less in the distance, right? So basically, if you can see that if the distance are shorter, so if you have shorter, closer to this, or you have more data points with shorter distance, then there's a more chance of having a higher accuracy in your classification, right? So if we look at the 5 of them together, you can actually say, well, we can say that 3 of them are German Shepherds and 2 are Huskies, right? Froze again, give 1 second. Good, with that. So we say 2 of them are Huskies. So in that sense, we can more or less say that somewhat we have more confidence because most of the neighbors are German Shepherds. We can have more confidence that it is a German Shepherd instead of Husky. So basically, that is how K-nearest neighbor work. And it is a very common and powerful machine learning algorithm. And basically that is mainly because you can use it to sort out a lot of things beyond dog. And it's quite lazy because it helps you do the bulk of the classification more or less in a very short instance. If you've got a really powerful computer to do your processing for you, right? It is mostly used in the finance to look at things like stock or the best stock to go for. So if you're interested in stock market, and also you can use it to predict things like even future performance. Are we okay up to this point? Are there any questions?
Yes, please.
Ask.
Yes, please. He has a question.
Okay, so I'd like to know what metric we use to measure the closeness of the neighbors.
Okay, so basically it's Euclidean distance. So if you have the x minus the x, which is x of the ground truth data point, so you have, let's make that st, or TX, just read out, and then the unknown as well. And because you don't want negatives as the end results, you're just going to square that. And again, you do the same for the Y as well. And you do you square that, and eventually you find the square root of that, which is the Euclidean distance. We come across the same metric or the same calculation at some point today anyway. Yeah. Are there any other questions, or are you happy for us to continue?
Hello, I also have a question. Please, for the side that you've circled, what if the notes were like equal? Like, how do I say, the nearest one, what if they were all equal? You said the nearest one from the green data points is 5. What if it were like maybe 2, 2, so like 4? I don't know how to say it.
I think I understand your point, and I was trying to draw in the machine for. Okay, there we there. So I think you're trying to say, what if we have that? Number one, just remember that this is supervised, and we decided a K to use, right?
Please, I didn't get you.
Yeah. So if I understand you correctly, all I've said is, if I understand you correctly, what you mean is something similar to what I've drawn on the screen, where our circle, we have like 6 surrounding it. Let's say if we chose a K of 6, and then we've got 3 German Shepherds, 3 Huskies, and 3 German Shepherds, for example. And I'm saying in the first instance, just note that we decided what to use for the K.
Oh, okay, yeah,
right.
Yes.
So we had a role to play in the outcome in here as well. So our decision has affected the output, and of course there are different ways that you can evaluate the performance of your the results of your work as well. I mean, we've done something similar to when we use the confusion matrix and other things to evaluate the confidence, and eventually you choose which one works best for you. So you still have a decision to make as the ML expect.
Oh, okay.
Yeah. Are you happy for me to continue, or you want a quick comfort break now so we can continue to the end after the comfort break?
Michael, please, another question.
Yes, please.
There was
Hello,
a go for the question before clarifying.
Yeah, when does the condition of the mixed breed come in?
Sorry?
The mixed breed, when does that come in?
Okay, so if we step back, at the moment, we just interested in understanding how the KNN work, right? So if we understand that basis, the fact that we simply look at the distance when we are dealing with KNN, and we are choosing the minimum distance to it, but of course, Euclidean distance in this particular case. Once we, or most of us, understand this concept, I'm happy up to this point, then I can answer your question.
Thank you.
Okay, so in real world, of course, there are several other predictors you can use, but we decided to use only 2 predictors to make life easy for us, so we understand how the KNN work. And based on the predictor you use, you are likely to have different results as well. So mixed breeds probably have different hair lengths, and that's based on the data you are feeding into the system. And remember, this is supervised data, so you will have a better understanding of the data, and you can tell how mixed breeds look like in order to feed it into your model to train it. Does that make sense?
Yeah.
Okay. Do we want a quick 5 minutes break?
Yes.
Break? Yeah, and then come back refreshed, then we continue. See you in 5 minutes.